Assalamu alaikum. This is Munammil Ejaz. I have covered power plant labs of section E and some labs of A. Well, the purpose of recording this video that we merge three different subjects in single workbook, so it's very difficult to cover a whole, especially that last experiment, gas turbine, and unfortunately, it is not in working. The exhaust system is in the process of laying and commissioning, but before that it is in the running, and I've done this practicals, not practicals, but I've done this gas turbine and show observation to the last year third year students. So I have video, and right now I've done calculation too for its efficiency, specific fuel consumption, and its thrust. Okay, so let's start. This is gas turbine. Basically, it is not designed for gas turbine. It is consist of two turbocharger. Connect with the gas turbine. Connect with the combustion chamber to produce some sort of a gas turbine. That's why its efficiency is very low. Its thrust is very low. Anyway, the air is coming initially when we start the system. They initially come from this way. This it has a blower which start this engine, and when the blower is run electrically, like your cleaning blower, etc., is something like that. Okay, so air is forcing towards this compressor. The compressor run, compressor run, and compressed air goes into the combustion chamber. On the top we have a fuel inlet and a spark plug. The spark plug glow, and this box having a sensor that this is the spark. This is the combustion sensor. When the combustion take place, the sparking stop, and both air and combustion gases goes into the turbine, and the part of the turbine, the part of the combustion power goes directly to the compressor. The compressor and turbine is connected with each other. Okay, and the remaining thrust goes into the next turbine. This is also a turbocharger, but it taking only turbine part. Okay, so part of the energy converts into the shaft power, and that shaft is connected with the belt and pulley to below electrical generator. This is DC electrical generator, and we have bulbs around comprising of 500 watt. And if we increase the speed, the power is increased. If we have a lower speed, the bulb glowing is very low, and we have a less power outage. Below this we have two heat exchanger to cooling out the system. This one is a Shannon tube, and the bottom one is a plate type heat exchanger. Okay, they both connected parallel. This is oil sump, and we have pump. The pump the pump makes high pressure, and that high pressure goes to the bush bearing of these two turbochargers. Okay, and then hot oil again, after getting hot from this high speed turbine and compressor shaft to the heat exchanger, cool down from the tap water, and again collect into the sump that recirculate the oil. Okay, both turbine, this turbine is working RPM is around 1,20,30,000, but the secondary turbine is generating power, so it's low RPM turbine. I'll show the parameter like 30-40,000, and that further reduced to 3,000, 4,000, so on, by belt and pulley system. Okay, so this is the system. Let's go to the real diagram. This is comprising the flow sensor and all things. We have propane gas, that is not a pure propane, it's a mixture of butane and propane called LPG. Okay, so that LPG goes to the combustion chamber by this flow knob, and this flow knob also showing the flow of LPG that later used for its thrust calculation and power calculation, efficiency calculation. Okay, so this is the schematic. This is blower. Initially the blower start the compressor, and then 100% combustion is done. When it's having a sustainable temperature, this compressor stop, and it naturally takes air from the air vent. we have a damper. First, the damper is closed when it takes air from its natural compression, so the blower stops. So air compressor sucking the air goes to the combustion chamber to the turbine. Turbine makes power to run this compressor, and remaining thrust goes into second turbine. Okay, this is shell and tube heat exchanger, and this is a plate fin heat exchanger for cooling this unit. This is oil of a port turbines. Okay, so I hope you are understand the working principle of this turbine. Well, coming to the parameters, this is basically operational parameter for turbine. It is linked with the SCADA, controlling and observing their values. Okay, so ST1, you can see that ST1 initial temperature, ST2 is after compressor temperature, ST3 combustion chamber. This is ST4 after turbine, first turbine, ST5 after second turbine, and so on. And this is the pressure parameters. SP1 is a ambient pressure, SP2 after compressor, 3 after combustion, and so on. And SV1 is the RPM of the first turbine, and SV2 is the RPM of second turbine. We have SF unit coming into the Newton, but it is not calibrated. I think it is not up to the mark. I do manual calculation, but the values is not same. And we have a current from the electrical generator and voltage. Multiply with this, we get electrical power. That's a DC power. This is the starting operation. We start this turbine. The first this fan will start. Check the basic pre-start alarm like sparking, gas, oil pressure. After that, when it having a sustainable temperature, it goes we click self working, then blower stop, it suck air naturally. Okay, so these are the working parameter. You can see that in the manual. We have 19, let's suppose 19 temperature, ambient temperature, 65 is compressor, and 650 after combustion. After first turbine, the temperature loss and also pressure loss, we have 4.43 bar pressure after compression, and after turbine the pressure reduced to 0.39 bar. Okay, I think pressure is not calibrated up to the mark. It is not producing 0.39. Maybe it's working on low pressure, but it's up to 1 bar or 2 bar as per compressor characteristic. And you can see that RPM 1,52,000. The initial turbine is running on that RPM, and second turbine is running on only 2006 RPM. Okay, so now moving towards this is all about the turbine. Now come towards the main parameter which we need to calculate. You note all this parameter. Now you have to calculate the thrust, electrical power, and one more thing I should place over here, specific fuel consumption. Anyway, yes, gas consumption is not calculated by SCADA. I tell you the manual reading around 50 to 60, and I'll show the video too, which showing that it is running on between 50 to 60 liter per minute. The flow is around this gas flow, propane LPG gas flow. Okay, so yes, now comes towards the calculation. Where is the calculation gone? This is the calculation. Okay, so MF is the mass of the fuel. I'll show the fuel flow from this picture, I think. Yes, I'll share this picture. We have maximum limit of 80 liter per minute, but it is working on between 50 to 60. Okay, this shows the mass of a fuel propane LPG, and it is not recording electronically, so we have to put manual reading like 50 to 60. Okay, so we have taken, it goes here. Yes, this is the reading. Okay, we take, let's suppose take 50 liter per minute. So convert into the kg per meter cube, divide by 1000 to get in the meter cube from liter, and 60 to get in the second, and multiply by its density of a air at that temperature. I've taken some student parameter. Okay, like 33, I think they I take this density at 33 temperature. Okay, so in that case we get the answer from volume flow rate to v dot multiply by log, we get the mass flow rate. Okay, so this is wrong. This is not mf. This is the volume flow rate, 50 liter minute. This is mass flow rate by multiplying the density of air at that temperature. Okay. Now comes to the air flow rate. Air flow rate, we take the value from this parameter. I shared this file too. Okay, I'll share the reading and do calculation. I take SC1 from this point. Where SC, this is SC1. Volume flow rate of after compressor. So this is the before compressor. So this is air flow rate. Okay, and where it is, yes, this is air flow rate, volume flow rate. Okay, so mass from this is volume flow rate 1.42 meter cube per minute. So we convert into the second and again multiply by its density to get in the answer, to kg per minute, and then we calculate to kg per second. Okay, yes, we get answer kg per meter cube and then multiply by its density, so we get answer kg per minute. So this is mass of air 0.00158 kg per second. This is mass of air 0.084 kg per second. The total mass will be 0.08558 kg per second. So we got the volume flow rate of total, and the total volume flow rate is from this SC2. Okay, after combustion, after combustion we have both volume flow rate of like gas and air. Okay, so we take this value 21. I've shared Excel file now. Excel is not installed in my system. You can see student take this value for 21 and 4 from this Excel file. Okay, so we get velocity by dividing area. Okay, and the flow rate is in the meter cube per minute, so we can convert into the meter cube per second and then divide by its area to get the velocity. Okay, so we get the velocity around 5.33 meter per second. The thrust formula for internal flows only. For external flow, it's a whole formula like mass flow rate multiplied by VE minus VA plus A upon M, PE minus PA. We have momentum thrust and pressure thrust. You will see, you will learn that formula in next semester CFPS. Okay, so we got the thrust value 0.456 Newton, and from calorific value of propane 46360 kilojoules per kg, we multiply this with the we multiply with the mass flow rate of the fuel 0.0058. Yes, so we get the power potential of the fuel. We are burning 73.24 kilojoules per second. That much energy we are burning. And from how much electric power is taking, I taken this electrical power from this current into voltage. Multiply by this, we get electrical power. Yes, this is the conversion. Okay, so we have electrical power of 162 watt. We are getting some voltage around 50, 60 and some current. Multiplying this, we get value of 162. Let me show you Excel file. Assignment. Anyway, I've shared this file. Yes, this is, we take this 202 and current, multiplying this, we get this power 160. Okay, so these value taken from this Excel sheet. This is we have recording system of all parameter. So with respect to different time, the parameter is recording, and this is SC1, this is SC2, and this is SC1. You can see that SC1 is 0.4.4 and SC2 is around 21. Okay, so yeah, this is electrical power. That electrical power is in the watt. So this is the relation from 1 watt to kilojoules per second. 1 watt is equal to 0.001 kilojoules per second. So we get electrical power only of around 0.162 kilojoules per second. So dividing output divided by output, we have only 162 electrical power and 73.25 kilojoules per second we are burning the fuel. So we get only 20.22% of this electrical power after burning. It is very low efficient because it is not designed for the gas turbine system. The actual system I'll show you here. I just take out this actual system over here that I really intend to share during lab, but unfortunately we are very short of time because we have a very loads of practical in a merged in a single practical. Yes, the actual gas turbine is something like that. Even it is consists of same centrifugal compressor and a radial turbine. When I was in the English Biscuit Private Limited, we are intent to purchase this turbine, and it's very expensive but very highly technological advanced turbine. It for the 5 years it doesn't take any maintenance. Okay, and the system is like the air is come from this point, sucking the compressor suck this air, goes into the heat exchanger, taking heat exchange from exhaust gases, then goes into the combustion chamber, and that combustion chamber high temperature pressure gases goes into the that turbine, and after combustion the gases released from heat exchanger. That exhaust gases also heat the inlet air of after compressor. So it's a very efficient system. It efficiency like 50-60%, not 45, sorry. It's a very small machine. You can see in the initial this whole turbine is placed in this only cabin, and it producing around 1 megawatt of power. So you can see that because it's running on a very high RPM as per affinity law. If you increase the velocity, if you increase the RPM, you can reduce the size of the system. Okay, I'll share the simulation video. This is recuperator heat exchanger, and you can see that there's no part of a oil lubrication some kind of thing, because that's why it is a maintenance free system for a 5 years. Only you need to replace the filters, This main shaft, we have only one shaft connected with the compressor turbine, even in the with the generator. There's no coupling, there are no losses of power, and the whole shaft is lifted on air bearing. We have compressed air, we levitate this shaft with the cushion of air, so we don't need any lubrication kind of thing. That's why it's a very high efficient maintenance free system. And in the future, I believe that these type of turbines taking place IC engine. IC engine, I mean, you can see that in vehicles, the IC engine is taken place by electric motors, and you can see that the IC engine using for the power generation in our industry will be taken place by these type of highly technological advanced gas turbine machines. I'll show some my working on it. We taken quotation from Gandhara, the local company representing this caption turbine. When I was in BBM, this is offer letter, initial proposal. You can see that value of turbine is very high. It's around, on that time it's 12 crore rupees, but now the dollars increase. You can see that gas turbine, caption turbine, 0 to 12 lakh 35,700 dollar, US dollar. You can see, imagine how it's in the crore rupees, like 19-20 crore rupees right now. So this is all about that gas turbine. I hope you understand its working and its operation in the future. During your Viva, you must have complete this calculation and attach with your workbook. Okay, and you know all the things. Right now, I made the video. I hope you know every point which I explained in this video, and will able to give answer in the Viva. Okay, thank you. This is efficiency thrust. Place this values in your worksheet, practical worksheet. Okay, thank you. Oh, one more thing, last thing, the working videos of this turbine. Okay, this is working that last is final year student has running operation of this sector. You can see that major company, the light bulbs are going with this fluid flow. You can see that it's working on this turbine. The machines are not these are fuel, the RPM is very more with the high intensity. We have also okay. Okay, thank you. I stop this recording.